Hi everyone, let's have now an example for the maximum power transfer theorem. Let's recall the Thevenin equivalent circuit. It is a series combination of the ETH, RTH, and with the variable resistor RL. In our previous discussion, we derived value of RL such that there will be a maximum power transferred to the load. And from our derivation, we learned that the RL must be equal to RTH such that the power delivered to the load will be maximum. Of course, when we are given with a complex circuit, we need to solve for the RTH and the ETH using the Thevenin's theorem. And when we will get the value of the RTH, that's automatically the value of the RL. We have here a graph that represents the power with respect to the RL. So at this point, this is the maximum value of power. This is the value of the peak power when the value of RL is at this point. You can see here, this is the maximum value of power. And when we drop down a line, a broken line here, this is its corresponding value of the RL, such that there will be a maximum power delivered to the load. As we see in the figure, in the graph, that when the RL is less than this value, then the power will be smaller value. When the RL gets higher value, so also the power will be a smaller value. So therefore, there is only one value of the RL that the power delivered to the load will be a maximum. It is in this point, of which this RL is equal to the RTH. Example number 1, refer to the figure shown. Determine the value of the load resistance to be connected across the terminals A, B. So we have here a variable load resistance. We need to determine how much is the value of RL such that there will be a maximum power delivered to the load. That's the unknown in letter A. And letter B, we need to determine the maximum power delivered to the load that we determine in letter A. Recall that we need to use the Thevenin equivalent circuit in order to find the RL, and that RL is just equal to the RTH. Let's recall the Thevenin's theorem. So we need to convert the complex circuit into a simple series circuit such that we will have a series combination of the ETH and the RTH, and then we put back the RL across the series combination of the ETH and RTH. So we need to solve for the RTH, and remember that when we solve for the RTH, we have to remove the RL and set all the independent sources to 0. After that, we have to draw the equivalent circuit. So to set the voltage to 0, we have to replace it by a short circuit. And then we have here the 20 ohm resistor. And then the current source will be replaced by an open circuit to set it to 0. And then we have the 10 ohm resistor. And we have this 20 ohm resistor. And of course, we have to disconnect the load RL. And then, what have you observed? The 20 ohms and the 10 ohm resistor are now connected in series. So let's draw the equivalent circuit. Disregarding now the open circuited terminals. Okay, this is now 20 and then 10 ohms. And we have here the 20 ohms. And this is the RO. At the open circuited terminals across AB, where we have to solve for RO. Therefore, we see here that the 20 and 10 are connected in series. So this RA We call it RA, which is equal to 30 ohms. And then if we simplify further the circuit, so it is now a parallel combination of the RA and 20 ohms. So then we can have the value of RO. RO is just the parallel combination of RA and 20. So we have 1 over RA, which is 30 ohms, plus 1 over 20. That's equal to, if we will compute, that's equal to 12 ohm resistor. So that is the value of the RO. The RO is also RTH. The next step is we have to determine or solve for the ETH. Recall how to solve for the ETH. So we just need to remove the RL and leave the terminals open. After removing the resistance RL, this is now the equivalent circuit. As we notice here that we have a current source in parallel with a 10 ohm resistor, and we have here the voltage source 115 volts in series with a 10 ohm resistor. Okay, so our interest here is we're going to solve for the ETH at the open circuited terminals. The simplest way in simplifying the circuit is we need to convert this current source into a voltage source. So the voltage E1 is equal to the product of 3.5 amperes and the 10 ohm resistor, and which is equal to 35 volts. And then we draw the circuit. So we copy the voltage source and the 20 ohm resistor. And then current source, which is to be converted to a voltage source. You observe here that the current source is, its direction is going to the left. Recall that the current will always come out from the positive side of the voltage source. So the voltage source now, from a current to a voltage source, we have here plus, because the direction is to the left, so plus, minus, and then the 10 ohms now will be connected in series with the 35 volt source. And then we have here at this terminal, we have the 20 ohms, and across the 20 ohms is the voltage ETH, which is the anode. Okay, we notice here that it's just a simple series circuit. So if we have to assume that the current that flows through the circuit is the I, and the terminals AB, no current flowing. So the current that flows through the 20 ohm is just the I. So you have here plus, minus. And we have to write the KVL. We will use KVL to solve current I. So we have 115 minus the 35 volts minus the sum of the resistances that the current I is flowing through. So we have 20, 10, and another 20. So you have 50. I that's equal to 0. So we add algebraically the 115 and the negative 35, so that is 80. So then we have minus 50i, that's equal to 0. Transpose of negative 50, it becomes plus 50i. And then divide it by the coefficient of I to solve for I. So cancel. The I here is equal to, if we solve it, that's equal to 1.6 amperes. Thus, ETH is just equal to 20 times I. If we substitute the I, so 20 times 1.6 amperes, then it's equal to 32 volts. Then, the Thevenin equivalent circuit, we have here the new voltage source, which is the ETH, the new internal resistance, which is the RTH, and across these terminals, AB is the RL. from our derivation that there will be only maximum power transferred to the load RL when the RL is equal to RTH. So RTH is just equal to 12 ohms, and that is the value of RL for maximum power transferred to the load. Solve for the PL max. So the PL max from the formula, we need to know that IL max squared times the RL, where IL max happens when RL is equal to RTH. So IL is just equal to, by Ohm's law, IL max is equal to ETH divided by RTH plus RL. Since RL is equal to RTH, then IL max is equal to ETH divided by 2 times the RTH. If we will substitute, the ETH value is equal to, 32 volts. And RTH here is 12 ohms. So since the value of ETH is 32, so we substitute it here. 32 divided by the 2 times RTH, which is equal to 12 ohms. And IL max, that's equal to 1.33 amperes. Therefore, the PL max, just substitute the value, so that is 1.33 squared times RL, which is equal to 12 ohms. And the value is equal to 21.33 watts.